Okay, this is a continuation of the practice test for MAC 1140 Pre-Calculus. We're talking about the topics on Exam 3, which cover sections 11.1 through 11.6. And this video kicks off with number 53. Okay, so in 53, 54, and 55, we continue to do partial fraction decomposition. We're hitting some of the harder cases now, so let's go with 53. Okay, so here's the problem. And sometimes, the denominators are factored already, and sometimes you need to factor them yourselves because that's going to tell you what your LCD is so that you can clear out all the fractions. It also tells you how to set up the fractions that you're going to decompose it into. So we're going to go and factor this. This can be factored as a quadratic trinomial. In other words, this degree is twice as big as this, so you factor it in the same manner as if it was x squared plus 5x minus 36. You take the square root of this term, which is just that power divided by 2. That's how you take the square root of a higher power. That would be x squared. Goes in the front position of each parenthesis. And then you think of two numbers by knowing your times tables that multiply to be negative 36, but when you add them, you get 5. Those numbers would be 9 and negative 4. When you multiply those numbers, you get negative 36, but when you add them, you get 5. Okay, so we are into the case where you have irreducible factors. In other words, you are not going to be able to get these factors any lower. One of these factors you can't get any lower than second degree. Okay, that would be this one. This is an irreducible factor. And that's because this one cannot be factored any further. This one can be factored further as x minus 2 and x plus 2. Okay, so we get into this problem and we come to a new case where we have a second degree factor that we cannot break down any further because you can't factor the sum of two squares. Okay, so now we have an idea of how to start decomposing our fraction. Any fraction that you decompose over here on the right side, if the denominator is linear, first degree, then it gets a constant as its numerator. So this is one of the fractions. This will be another fraction for the other linear factor, x plus 2. And for this irreducible factor, which you have right here, whenever it's a second degree, then the numerator will be 1 degree, an expression that's 1 degree less than that. So it will be a linear expression of the form where you have a first degree x term and a constant. This is what the numerators look like when your denominator is second degree. Okay, so new case as opposed to the 3 problems that we did regarding partial fraction decomposition in numbers 50, 51, and 52. Okay, so here we go, going with the steps that we have used for all these problems. As soon as we factor our denominator, decompose, assigning the proper numerators to each of the denominators that we get by knowing what the factors look like, we then clear out the factors by multiplying by the LCD, and that would be what you see right here. X squared plus 9 times x minus 2 times x plus 2. Okay, we're going to multiply that LCD by this first fraction, the main fraction over here on the left. Everything in this LCD would kick out all of the terms in the denominator, and you'd be left with just the numerator. So x squared minus 56 on the left-hand side. Then we're going to multiply that LCD by this fraction. The x minus 2 in this denominator would cancel with the x minus 2 here. You'd be left with x squared plus 9 times x plus 2 times a. These are all the things that don't cancel after you see that the x minus 2's cancel. You'd be left with a, you'd be left with an x plus 2, and you'd be left with that x squared plus 9. When you multiply the LCD times the next fraction, the x plus 2 from this denominator cancels with the x plus 2 in the LCD. So then you'd be left with x minus 2, the x squared plus 9, and the b. Okay, then coming to the very last fraction, multiplying this LCD times this last fraction on the decomposed side, this x squared plus 9 in the denominator cancels with this x squared plus 9. You'd be left with x minus 2 times x plus 2 times cx plus d. Okay. All right, so now we start trying to find these numerators. So one of the techniques that you've been shown is zeroing out, finding the value that zeroes out any of the factors that can possibly be zeroed out. You can zero out this factor right here using the x value -2. So we're going to let x be equal to -2. And then there's another factor that can be zeroed out. That would be this one. And that can be achieved by letting x be equal to 2. And this will hopefully help us find some of the values in the numerators that we have assigned up here. So here we go. Okay, we're going to let x be equal to -2. Use your calculator as much or as little as you want to, depending on, how much you like to do in your head. So -2 squared is 4. When you square a negative, you square the negative as well as the number. So it can't possibly come out to be positive. So it'll be 4, take away 56, which is -52. Again, pop that in your calculator if you need to. If you put a -2 right in here, it creates a 0, thereby zeroing out this entire first expression. If you put a -2 right here, that's going to be -4. And I'll put this in the calculator. Oops, get rid of that. Okay, so if I put a -2 right in there, it's going to be -4 times. When I put -2 in here, it's 4. -2 squared is 4. 4 plus 9 is 13. So I'd be multiplying by 13. Did wrong. Okay, -4 times, and this would be, let's see, what did I say? I said times 13. Okay, so -52. And that -52 would be multiplied by b. Okay, continuing. If I come over here into this last product of 3 things, allowing x to be -2 in this third factor would create a 0 here, thereby turning this entire third term into 0. Okay, so that is gone also. All right, so plugging in the -2 zeroed out the first term, zeroed out the last term, only this was left. So this is going to allow us to solve for b. Okay, we now know that b is equal to 1. Moving on with this same technique of using numbers that zero out certain factors, now we're going to let x be equal to 2. So 2 squared is 4. 4 take away 56 is -52. Moving to the right side, if I'm going to let x be equal to 2, that would be 2 plus 2 is 4. I'll keep track of it here. And then if I put 2 in there again, it would be 4 plus 9 is 13. So 4 times 13, 52. And that 52 would be multiplied by a. Okay, continue with allowing x to be equal to 2. If I put a 2 right in there, it's going to zero out this factor, thereby zeroing out this entire second term. So that's gone. If I go and put a 2 right in here, it appears there again. These factors that can possibly zero out appear in this one as well. So if I go and put a 2 in there again, it's going to create a 0 in this middle factor, thereby zeroing out this entire third term. So this is all I have left when I let x be equal to 2. So divide off that 52 so that you can solve for a. And you now know that -1 is equal to a. So we have 2 of the 4 values we need to complete this problem. We have the a, we have the b. We still need c and d. But we have exhausted all the values that can be used to zero out the factors. It is impossible to zero out that factor because the only thing you could add to 9, to a positive 9, would be -9, and there's no way to square any number and get any real number and get a negative. So you're done with this technique. Now we have to move over, as we have in the other problems, to comparing terms of like degree. So I'm going to compare. I think I will compare third degree. And that's because there's so little of it, so it's just the easiest thing to compare to start off with. When you're on the left-hand side, you have no third degree terms. You have 0 of this sort of term, so you write it like that. Over on the right-hand side, if you were to begin foiling this out, but not necessarily going any further than third degree, only because that's what I'm concentrating on right now, third degree. If you were to begin the foiling, this is where the third degree term would happen. You would only have that one third degree term. So it would be x to the third degree, which would eventually be multiplied by this a. Just recognizing all the third degree terms. If I was to begin this foiling process, it would be x times x squared. That would be your third degree term, which would ultimately be multiplied by b. And then in this particular product down here, let's see where the third degree term would be. Okay, let's write it out carefully here. So if I was to multiply x minus 2 times x plus 2, those are conjugates. So the shortcut for getting these multiplied out is square minus square. You can either be looking here or here when you do the square minus square. You just square the first term, square the second term, and put a minus in between. Shortcut for foiling out conjugates. Now multiply by the cx plus d so you can recognize the third degree term. Okay, when you go cx times x squared, that very first product in the foiling process would give you cx cubed. So you have yet another third degree term. And those are all the third degree terms that exist in this entire equation. So now once you have recognized and pulled out all the third degree terms, you work strictly with their coefficients. So it is 0 is equal to a plus b, taking off those coefficients, plus c. However, we already know the value of b as well as a. So a is -1, b is 1. We are looking for c. These cancel, and we find out at this point that c is equal to 0. Okay, moving to let's move to finding d now. Okay, so we now have a B, and C. And you can compare any of the degrees that you think are going to be easiest to pick out of the products that are happening here. You can compare second degree, first degree, or the constants. So let's see, if I was to try and compare the constants, let's just kind of talk about this, because yes, we could compare second degree or first degree, but there's a lot more of those terms possibly than there are of the constant. So let's see, if I was, here the constant's very obvious, negative 56. Over here, the constant would happen in that very last product that you do when you're foiling. You know how you go first times first, outer times outer, inner times inner, and last times last. Well, that last term would be 18A. So let's just consider what we're doing here. If we were going to FOIL this out, that last term would be negative 18B. We need something with a D in it because D is the only value that we don't know. If we come down to this last term, and we did part of it right here. So let's look at this, but down here. It would be cx times x squared, which is that x cubed term. Then you would have cx times negative 4. You would have dx squared. We're trying to think about the constants. And you would have d times negative 4. So I think I am going to compare those constants, and I'm going to do it right here. So I can conserve room here. Again, you have the option of comparing any terms that are of like degree. All constants are considered degree 0, so they're considered like terms. And the decisions that I'm making are based on what do I think I have the least of. There's more second degree and first degree terms, so you'd really have to get into the full foiling in order to pick them out of what's happening in this equation. I just thought that it's easier to pick out the constant, so that's why I've made that decision. All right. All right, so like I said, the negative 56 is the constant on the left-hand side. The constant here would come from the last product. 2 times 9 is 18 times A. The constant here would come from the last product in the foiling process, negative 18 times B. And then the constant here, I already did a more refined version of this. Here it is down here. And in this foiling process, we only talked about that first product in the foiling process. The last product gives you the constant. So that would be D times negative 4. Okay, so now at least we have an equation that has the one value that we do not know yet, which is D. We already know A, we already know B, and therefore we can put values in for A and B. A turned out to be negative 1, so that's 18 times negative 1. B turned out to be positive 1, so that's negative 18 times positive 1. And then negative for D, we'll be solving for D. So this is going to be negative 18 here, combined with negative 18, that would be negative 36 minus 4D. And then here it's negative 56. Okay, then I'm going to bring this negative 36 over here, at which point it'll be positive 36. This will no longer be here, leaving us with just negative 4D. Negative 56 plus 36 is negative 20. And then by the time you divide off this negative 4 to solve for D, you have D is equal to 5. And thus we have all 4 parts of the numerator, of the numerators. Okay, so I don't know that you need to write this main fraction, but you definitely need to get your head situated with regard to how those decomposed fractions are going to look like. So a gets assigned to x minus 2, and my a value was -1. So that's what one of your fractions should look like. On the right-hand side of your decomposed baby fractions, the value b gets assigned to a denominator of x plus 2. And you can see that right here. So let's pair up the b value we found with x plus 2. And the b value turned out to be 1. Then both the c and the d value get paired up with x squared plus 9. So it goes cx plus d over x squared plus 9. Okay, so my c value was 0. So when I go c times x, that x term will no longer be there, and all you'll have left is the d value. And that's just because c turned out to be 0. So when you plug it in here, this would be 0 times x. In other words, that wipes out, and you're just left with the d value. So in the end, this is your final answer. The main fraction would go over here if they, were making you write that. Okay, so that is 53. That was a free response answer. Okay, so let me make sure that's correct. It is. Okay, so moving on to 54. In problem 54, we get into more of this irreducible situation where we have second degree denominators left over even after we've attempted to factor. And that you'll see that as I try to factor this denominator. So if you remember the formula for factoring the difference of cubes, you take the cube root of the first term, you take the cube root of the second term. That sign that's in between them is what goes in the first parenthesis. And then it's square multiply square on these items right here. That's the formula for getting the 3 items in this longer parenthesis. Square multiply square off of these 2 cube roots right here. So square that first cube root, multiply these 2 cube roots, 1 times x is x, and then square that second cube root that you got. The signs in the longer parenthesis, well, this sign is the opposite of this one, and the last sign is always positive. So there it is, all factored. You need not look at that anymore. You need to look at it in its factored form. And that tells you how to begin the decomposition process. So this factor, being that it is linear, gets a constant as its numerator. And then anything that is second degree and can no longer be factored any further is what we call an irreducible factor. You just can't get it down any lower. And anything that is second degree gets a first degree expression. Oops, I can't use a again. First degree expression as its numerator. So it'll have an x term with a constant, with a coefficient, an x term with a coefficient, as well as a constant. So this should be, let's see, I used A, B, this will be C. Okay, these are the constants that I'm using. Pure constant for the linear factor, and then a linear expression, the x meaning an x term with a coefficient and a constant for anything that is second degree. And that's that irreducible factor. Okay, and we continue from here. Once you've decided how you're going to decompose this main fraction and what kind of numerators they should have, then you multiply by the LCD. The LCD is just this factored denominator in the main fraction. So x minus 1 times x squared plus x plus 1. Okay, when you multiply this LCD times the main fraction, the entire LCD kicks out the entire denominator, leaving you with just 3x minus 2. When you multiply the LCD by the next fraction, this x minus 1 right here cancels with this x minus 1 in the denominator, leaving you with a times x squared plus x plus 1. A times the expression x squared plus x plus 1. Next, multiply the LCD times this fraction, and this expression x squared plus x plus 1 cancels with this expression x squared plus x plus 1. And you're left with bx plus c times x minus 1. Okay, so now we have no more fractions, and we go about the business of trying to figure out a, b, and c. We need to find those constants, or those values, because this b plays a role coefficient, that's a constant, that's a constant. So one thing that we can get by recognizing values that zero out the factors would be to look at this linear factor right here. And note that if you put a 1 in here, it's going to zero this out. So let's go with that first. We're going to use the value x equal to 1 and see which of these values we get. So when x is equal to 1, it's 3 times 1 is 3. 3 take away 2 is 1. When we let x be equal to 1 here, b1 squared is 1, plus 1 more is 2, plus 1 more is 3, 3a. When we come over here, allowing x to be 1, we would get b plus c. And then if we were to put the 1 right in there, we would get a 0. So let's not even write that then. If we were to put a 1 right in there, we would get a 0. 0 times this, that whole term would be gone, so I'm not going to write it at all. So these are the only terms we need after considering what completely zeroes out. And this last term, after I plugged in a 1, caused a 0. This times this, that's gone. Okay, we're left with just this, and then dividing by 3, we get a is equal to 1/3. Okay, then, after we've used all the values that zero out, now let's start comparing like degrees. So we can compare second degree terms, we can compare first degree terms, we can compare constants. So we do have to find b and c. So let's say that we compare second degree. I'm going to compare second degree, because it's the first term that evolves when you're in the foiling process over on the right hand side. On the left side, there is no second degree term, so we have 0 of the second degree term. On this side, you have this one second degree term in this expression times a, so that's one of your second degree terms. Furthermore, if you were to begin the foiling process going first times first, you would get bx squared, and that would be your only second degree term having a coefficient of b. Okay, once you have picked out all the second degree terms on the left and the right hand side, work only with the coefficients. So 0 is the coefficient of this second degree term, and then we have a plus b being the coefficients of the second degree terms over here. Okay, we already know the a value, and this is going to help us to find the b value. If we were to bring this b value over here, it would simply appear as a negative 1/3 on the other side. So b is equal to negative 1/3, and we have two values now. Okay, then looking for something that's going to allow us to get the C value, you can go after the X term or you can go after the constants. Let's see if the constants would do it for us. If we need something that's going to have the value C as part of the equation. So we have a constant of -2 here. The constant here would be 1 times A because it doesn't have an X in it. The constant here would be the last product of the foiling process. Just like the first product is bx squared, the last product would be C times -1. So that does involve the C value, which is the only thing we still need. So I'm going to do that. I'm going to compare constants. And it's just easiest to go after the highest degree in the equation and the constant. I mean, sometimes if the problem's hard enough, you're going to have to compare all degrees to get all the values that you want. So I'm comparing constants. And I have a constant, like I said, of -2 on the left-hand side. On this side, 1 times A is the constant. In this product right here, you get the constant from the last product of the foiling process, which is -C. So it's -2 is equal to the A value minus C. If you're going to solve for -C, you need to bring this over here, at which point it becomes -1/3. -2 combined with -1/3, since they have the same sign, you just add them and attach that common sign. And you can write this as a fraction rather than a mixed number, so that it looks a little bit better when you're writing your numerators. It would just be 2 times 3 is 6, plus 1 is 7, 7/3. And that is your almost C value, because there's still a negative in front of the C. So right now we have -2 and 1/3 here, which is the same thing as -1/3. And if I want to completely solve for C, I have to divide off that coefficient of -1. So that gives me positive 7/3 as my final C value. I now have all 3 values, and so now I can write the numerators of my partial fraction decomposition over on the right-hand side of this top equation. A gets paired with x minus 1. That A value was 1/3. So that's part of the answer. B and C get paired with x squared plus x plus 1. So it's bx plus c. So bx plus c, belonging to a denominator of x squared plus x plus 1. That is the main fraction all decomposed. Let's see what, if this was, this may have been multiple choice for 54. And there we go, right there. That is D. We have 1/3 for the x minus 1 and -1/3 plus 7/3 for the x squared plus x plus 1 denominator. Okay, so 54 is D. Okay, last one for partial fraction decomposition. So here's 55. Again, what we've been practicing in these last few problems is the harder case called the irreducible denominator. Something that you cannot break down to first degree. Such is the case here. Now we move it up even a notch further, because now we have an irreducible factor, but it's repeated. Remember, there's the cases where things are repeated and the necessity to build up to this repetitive power, 1 degree at a time. So when this is all factored, you can't factor that any further because it's the sum of two things that you could actually take the square root of. I mean, you would have a radical in there, but you cannot factor that any further to first degree. So you can start decomposing, but you have to build up. This is a repetitive irreducible factor. So don't try to break it down any further. And because it is an irreducible factor, it's those numerators that you're going to assign to them cannot just be a constant, it has to be a linear expression like this. Ax plus b assigned to the irreducible factor of x squared plus 3. But right now we're talking about it to the first degree. That's why I'm not putting a parenthesis around it, because it's just to the first degree. Next, we'll build up to second degree on that irreducible factor. And it also gets a linear numerator. But the values will be c for the coefficient of x and d for the constant. This time we're talking about that irreducible factor of x squared plus 3. But now building up to power 2 rather than power 1 that you see it to in the first denominator. Okay, so now we have the decomposition going on. We bring our LCD out here, which is always just whatever this denominator is in the main fraction. And we begin multiplying to kick out the fractions. When you multiply the LCD times this first fraction, this LCD completely cancels with the denominator, leaving you with just the items in the numerator. And that would be x squared plus 6x minus 3. Okay, then you're going to multiply the LCD by the next fraction. This 1 x squared plus 3 to the first power. I'm not going to write power 1 there. That 1x squared plus 3 cancels with one of these x squared plus 3's, and then you have one left over. So you have an x squared plus 3 left over times a x plus b. And it doesn't matter which of these you write first. You can write this first and then this, or vice versa. You're going to multiply them together anyway. Okay, then we're going to multiply this LCD times the last fraction, and that LCD completely cancels with the LCD here, leaving you with just what's in the numerator, cx plus d. Now, because the factors in this main denominator involve nothing but irreducible second degree expressions, you will not be able to do any of that. Oh, let me find numbers that zero out the factors, because that only works for linear factors in this type of problems that we've been doing. So you got to go right to comparing like terms. Okay, so we can compare second degree terms. We can compare third degree terms. There is very little of the third degree term. Like, for instance, notice that on this side there are no third degree terms on this side whatsoever. So there are, let's see what we get when we pick out all the third degree terms. Will this help us to get one of the values? Move this. Just write a little bit better. Comparing third degree terms. So I'm going to go, I have 0 of the third degree term on the left side of the equation. And then over here on the right side, if I begin the foiling process that's suggested right here, I would have x squared times ax, and that would be ax cubed. If I come down here, there are no third degree terms, so very little of that third degree term. Once we have identified all third degree terms, we work simply with the coefficients, and right away we find out that a is equal to 0. So we know that value. Now let's move on. We can compare second degree, we can compare constants, we can compare first degree. Let's see, if we were to compare second degree. We'll definitely go and compare those constants, I think, but let's just see what this leads to. Second degree, we have one second degree term. We have a second degree term with a coefficient of 1. Over here, that was third degree. Here times x squared times b, if we continue the FOILing process, would be, whoops, this was my second degree term on the left side of the equation, so let me put that equal sign. X squared times b would be bx squared. And then let's see, if we continued the FOILing process, it's first times first, outer times outer, inner times inner. That would just be x to the first degree, and that would be a constant. So that's all we get. The only second degree term that we get right here is bx squared, and there is no second degree term here. So that's pretty nice. Now just compare, take off the coefficients. These are all our second degree terms. Work just with the coefficients, and right away you know b. So we know a, we know b. Now we have to go after c. Let's see if we can compare the first degree terms. See where those come from. On the left side, we have one first degree term and its coefficient is 6. Moving to the right side, we have that third degree term, that second degree term. We have this first degree term right in here, 3a times x. And then, of course, that last one's a constant because it has no x. Then over here, the first degree term is this c times x, a positive c times x. So not too bad because we already know the a value. So don't forget, once you've identified all the first degree terms, then you simply work with the coefficients, which is everything. You just drop the x's and use everything else. Okay, we already know that a is 0. So this would be 0 and c would be 6. Now we know 3 values. Going in for that last value, we have nothing left to compare but constants. So that's what I'm going to compare now. Okay, so we have, let's see, constants over here, -3. Constants on this side, it would be the last product of this FOILing process. Last times last, which would be 3b. And constant here is d. Okay, b value, we already know it's 1. So this is 3, this is d. Subtract 3, subtract 3. In other words, bring this 3 over here and you'll be subtracting 3 from both sides. And you end up with d is equal to -6. And that's all 4 values. So now when you go to break down your fractions, on the right hand side, you decompose them. You can just look at what you have written up here. For your x squared plus 3 to the first degree, you have ax plus b as the numerator. So a was 0, so a times x would just be wiped out because this value was a 0, so that's going to be gone, and you're just going to have b over x squared plus 3. The b value was 1. Okay, that's one of your decomposed fractions. Plus, for the denominator, that was x squared plus 3, but to the second degree rather than the first degree. You have a denominator of cx plus d. Cx, c turned out to be 6, plus d, the d value turned out to be 6. And this is your decomposed fraction. So for number 55, let's see, 1 with the x squared plus 3, and then it was 6x minus 6 for the x squared plus 3 to the second degree. So for 55, that is B. Okay, so that completes all the problems on partial fraction decomposition. We now move to the last batch of problems, which is solving the system using solving systems of nonlinear equations. So they're a mixture of, some of them might be linear, maybe both of them are nonlinear, but they involve nonlinear equations. We're talking about using substitution or elimination. The graphing is only to be used to check your answer. It was only offered in the lectures as a demonstration of how to verify your answers. Now you can put those into your calculator, but Desmos.com, that website that I introduced in the lecture, is even nicer because you don't have to solve for y in either of your equations in order to go and put the equation into the calculator. You don't have to use second calculate and try and move the cursor around until you get close to each of the, sometimes there's 2 points of intersection, sometimes there's 3 points of intersection, and you don't have to keep going into second calculate over and over again and moving the cursor around and sometimes jumping off the graph when you're doing that. So it could get very time consuming. In the TI-83, it's super easy using Desmos. So that is what I demonstrated on. And I think there's only one problem, number 60 in this practice test, where they talk about graphing. But you can, you can use Desmos.com to check any of your answers. All right, so let's move to next problem. All right. Okay, here's 56. So in 56, the instructions say, solve the system using substitution. Same thing for 57. So when you're using substitution, you can solve either for x or for y, and then you plug it into the equation above it and continue from there. In this, it's no easier to solve for x than it is to solve for y. Sometimes there is a difference in the option that you're pursuing, and so you go after the easier option. So if I do come to a problem like that, I will, share my thoughts with you on why I'm going one way as opposed to another way. But here, either one's good. I'm just going to solve for x. Okay, so I'm going to isolate the x by pulling this y to the other side, which would make it 11 minus y. When you bring this over here, it's a negative y, and you can write it as 11 minus y or negative y plus 11. I like to write my positive term first. Okay, now you're going to substitute. And you're going to substitute into the equation that you have not yet worked with. And you're going to substitute it in for this variable that you have isolated. Okay, you're going to substitute this expression for x in the other equation. So it's x squared plus y squared is equal to 61. Because what you're doing when you substitute is you're getting rid of one of the variables so that you only have one variable and thus can begin the solving process. So we're going to put 11 minus y in for x. I just opened up a blank spot where the x was. Okay, I'm going to use the square, double, square shortcut for foiling, because this is really foiling. It really means 11 minus y times 11 minus y, which would which would require the FOILing process. This is the shortcut to that, so that you don't have to write it out twice, use all the arrows, combine like terms and all that stuff. It cuts out like 3 of the steps. So squaring that first term is 121. Doubling the product, you're doubling the product of the two things that you see here. So negative y times 11 is negative 11y, but then you're doubling that number right out there, the coefficient, to give you negative 22y. Now square again. When you square negative y, you get positive y squared. So I just got all of this square FOILed out. There's an additional plus y squared, an equal sign, and a 61. You now have an equation with no x's in it. Okay, so now we're going to try and clean this up. 1y squared and 1y squared would be 2y squared minus 22y on our linear term. So I did that one, and that one. I have a 121, and I'm going to bring this 61 to this side so that we have everything on one side. Okay, so 121 minus 61 is 60. Positive 60 is equal to 0. All right, so now let's see what we can do here. If we're going to try and factor this, and let me just bring this to the middle of the page so I don't have to keep cramming it over here. Let's move this over here. So 2y squared minus 22y plus 60. Each of the coefficients here is divisible by 2, which the smaller we make them, the easier we'll make our factoring procedure. So let's go ahead and do that. We're going to divide all of this by 2. Therefore, we have to divide this side by 2. That would make this 2 divided by 2, 1y squared. It would make this negative 22 a negative 11y, and it would make this a 30. 0 divided by any number is 0. So now our factoring process is not going to involve splitting the middle term. We can just do guess and check when the coefficient of the squared term is a 1. So take the square root of y squared, it is y, and then ask yourself, what can you, two numbers can you multiply to get 30 but add them to get 11? That would be 6 and 5. As long as both of them are negative, it will satisfy both of the requirements for these two numbers, that you should be able to multiply them to get this back number, but add them to get the middle number. That's the guess and check procedure for factoring. All right, so then we end up getting the zeros here. What would make this 0? 6. And you can just find these two values by observation. I'm just writing it out. What would make this 0? 5. Now we have to find the x partners that go with these values. Oops. And if you want to find the x partners that go with these values, all you have to do is plug in these y values into an equation that also has x in it. It needs to have a y in it so that you can plug the 6 in, and it needs to have an x in it so that you can solve for the x partner. So the easiest equation to work with would be this linear equation because it doesn't have all these squares on it. So that's the easier way to go here. So working with this, continuing to try and find the ordered pair that serves as a solution. You're really looking for where these two graphs intersect. So if you're looking for where these intersect, you know, you find the exact answers by substitution or elimination, and then I'll show one of these on the calculator, but like I said, I recommend that you go into desmos.com. I'll do this one in the calculator though. Anyway, so let's go find the x partners. Okay, I'm going to take x plus y, which was that bottom equation. X plus y is equal to 11. I'm going to plug in the 6 for y. and solve for x. So if you bring this over here, you get x equal to 5. So one of the places that these two graphs hit is at x is equal to 5 while y is equal to 6. I just got this x value by allowing y to be equal to 6, so they are partners. They are an ordered pair. Likewise, for this solution right here, I want to let y be equal to 5 this time, using the same equation, x plus y equal to 11, which was the easier of the two equations, and plugging in a 5 this time for y. So x plus 5 is equal to 11. Move this over here, and you get x is equal to 6. Okay, so this is 6 for x, while y was equal to 5. Okay, and those are your two solutions. Demonstrating this on the calculator. Okay, so if you're going to do this on the calculator, it's kind of a pain in the TI when you have the second degrees. You have x squared plus y squared. This is a circle. When both terms are squared, they're both positive and both have the same coefficients. Those are the characteristics of a square. However, the reason it's kind of a pain to graph it is because you have to solve for y, and you don't have to do that in using the Desmos site. So real quick, just going to go y squared. I'm going to bring that x squared over to the other side, which will make it negative x squared. Then I'm going to take the square root so that I can solve for y, which forces me to take the square root on the other side. But when you take the square root on the other side, you have to report both the positive and the negative root. You can't just take the square root of that expression on the other side. Here, it just makes the square go away, and you get just y. You move this over a bit. This positive square root of 61 minus x squared is going to get you the top of the circle, and the negative square root of 61 minus x squared is going to get you the bottom of the circle. That's just one of your graphs. Okay, this will be y1 in our calculator. The other one's easy. It's just x plus y equal to 11. So by the time you bring the x over here, it's just y is equal to 11 minus x, and that'll be our second function. So putting this in the calculator, we're going to go to y is equal to, clear out whatever is there, go up to y1 and press in, and actually this is going to be y1 and y2 because we have to enter this as two separate functions, and then this 11 minus x is actually going to be the third function because circles have to be entered in two pieces, what produces the top of the circle and what produces the bottom of the circle. So this will produce the top of the circle, square root of 61 minus x squared. Close it, jump to the next one. Same thing now, but with a negative in front of it. Now give the negative square root. 61 minus x squared, close it, and then that third function is 11 minus x. Okay, then let's see. I'm gonna do a standard window and see if that works. I just press zoom, picked a standard window. That just means a 10 by 10 window. Okay, there's a circle. It doesn't look circular because if you wanted it to look completely round, then you would have to choose what's called a square window. See when you go to zoom how one of the windows is zoom square? That'll make your circle look completely round. No, there's just another representation. But anyway, the whole point is just to figure out where do they intersect. So if you want to find out where this line intersects with the circle, it looks like a point of tangency. So let's see, answers there are, but it's not really clear on the graph because it could cut through this graph, come underneath, and then come back out the circle, and it might not be so visible here. We already know, see, the procedures of substitution and elimination, they are dead on if you don't make any arithmetic errors. We already know that there's 2 points of intersection, that it hits at 5, 6, and that it hits at 6, 5. So that's why your actual algebraic techniques are more detailed and correct than what you might be able to see on the graph. So there's probably a point of intersection here, which is probably the 5, 6, and this is probably the 6, 5, a little further down. And you would, if you wanted to find them on your calculator, you could go like this. You could go second, calculate, which is the trace button. You could go down to point of intersection. It'll say, let's try to find this one up here, and then it probably comes out through the circle again somewhere down here. So when it says first curve, it means is the blinker on one of the curves? Try to get closer using the sideways arrows on your calculator. Try to get a little closer to the point of intersection. I'm going to go right there. Press enter to mark the point. Then it'll say, am I on the second curve? So now you want to get your calculator to jump to this second curve. So let's see if we can get it to jump to the second curve. That's the pain of it also. Oops. Okay, so I lost track of it. There. When you use these up-down arrows, you can sometimes get it to jump onto the other curve. And then the sideways arrows will make it travel along that curve. So there, I'm getting close to that point of intersection. I'm going to mark it again by pressing enter. Then your calculator will say, do you want me to guess at the point of intersection? Yes, I do. And we already know what the answers are. That's assuming we didn't make any mistakes when we did our algebra. And there you go. That's one of our answers. And if you want to find this other point of intersection that's a little further down, which I only know because this answer is 5, 6, and the other one was a little further out, 6, 5. It's a little further out and it's a little lower. So you would have to try and hover around here if you wanted to get the other one. Now, I don't know if we can get that one, but you would have to press second calculate to wipe the slate clean of all the work that you just did to find the first intersection point. This is kind of a hassle. And let's try and get closer to this point down here. So let's go these sideways arrows, move closer to down there. Let's mark that as being on the first curve. Okay, now it'll say, am I on the second curve? There's the blinker now. Move closer to where you marked this point. You marked a point on everything's called a curve. The line's called a curve, the circle's called a curve. That's what your calculator calls your graphs. So it's saying, am I blinking on the other curve? At first you were on the line and you marked it. Try to get closer by using the sideways arrows. You're already on that circle curve. Okay, I'm going to mark that. Now it'll say, yep, I thought I pressed enter already. Maybe I'm not on the second curve. Would you like me to guess? And nope, nothing. All right, let's see if we can do it again. So second, I'll try it one more time, but I'm not going to invest too much time in this because I've got to finish with this intersect. All right, so it'll say, am I on, first curve just means, am I on one of the curves? I'm trying to hover around this point right here. So try and get a little closer. mark it. Okay, then it's going to say let me see what a marker is. There it is. Okay, so it definitely looks like it's on the line to me. So that'll be my first curve, and I'll mark it. If it doesn't work this time, I'm just going to say that we've done enough by doing the algebraic portion of it. Use Desmos.com. It'll be tons easier. So that's it's on one curve. Now it'll say I'm on the second curve. Let me see if I can jump off of this curve and onto the other one. Let's see. Doesn't want to jump off of it. There, it's definitely on the circle right now. So let's see. See if I can get closer. I'm going to leave it right there. I press enter. It'll say guess. No sign change. Well, okay, so I'm going to leave it like that. This is the other answer. I verified one of them on the calculator. Try it on Desmos.com. You'll get both of them. Okay, so let's go on to number 57. Okay, so 57 was another one for substitution. And again, let's see. We can either solve for y. I think that would be the easier way to go. Because if we solve for y, we're going to get 8 minus x, and we can pop it right in there. Whereas if we solve for y, we're going to get 8. No, let me see. If we solve for x, we're going to get 8 minus y, and then we'd have to put it in for x and then end up having to square it. That's the harder way to go. So if you can plug in for something that's linear, first degree, go with that choice. Solve for that variable. I'm going to isolate y. Okay, that just means I'm going to have to pull the x over here, and this would be y is equal to 8 minus x. Okay, then I'm going to do my substitution portion of the problem. Going up to the top equation, and right in there for y, I'm going to plug 8 minus x. Okay, I just plugged this in for y. Okay, I put it right in there, and now I'm going to copy the rest of this. X squared minus 4x plus 4. Okay, you have a second degree equation in x, therefore bring everything to one side. Bring this to the other side as well, and factor it. Okay, so everything is gone from this left side. It's all over here on the right-hand side. You have a squared term. You have negative 4x plus 1x is negative 3x, and you have 4 minus 8 is negative 4. If you go to factor that, that's going to be x, and then you'll have negative 4 times positive 1. This times this is negative 4. This plus this is negative 3. So it's factored properly. And then if you if you want to know what zeroes this out, you can just do it in your head. It's negative 1. Or you can set x plus 1 equal to 0 and solve it, and you'll still get negative 1. What makes this 0? X equal to 4. So those are the solutions for that equation. You now need the y partner that goes with this x value, and you also need the y partner that goes with this x value. So you're going to keep going until you have complete x, y ordered pairs. Okay, easier equation to substitute into at this point would be the bottom equation. So I'm going to continue there. I have x plus y equal to 8 as my second equation. One of my x values is -1, and the y partner that goes with that would be, bring this over here, it becomes +1. So y partner is 9, giving me a complete ordered pair of -1, +9. Then we can use that same equation and we can go x plus y is equal to 8, this time using the x value of 4. Bringing this over here, it becomes -4, and you end up with y equal to 4, giving you another complete ordered pair of 4 for the x and 4 for the y. And those are your two ordered pairs. Again, you can check them by graphing both on Desmos.com, and you'll be able to just click on the points of intersection, and it'll highlight the solutions that you just got, serving as an answer key for what you're doing here algebraically. That's 57. Coming up on a close to this practice test. We're getting closer. Now we move to 58 and 59. And in 58 and 59, they ask you to use elimination. Elimination, when these problems are all mixed up together, and I went into this quite a bit every time I did a problem from section 11.6 in the lecture notes. When you see that all your variables are the same degree like this, it is most probably the elimination method that's going to be the easiest way to get to those answers. But when you're in a problem like this, like what we just did in 56 and 57, where one of the equations are first degree in their variables, while there are second degree terms in the other equation, in some of the variables, then you're doing substitution, because they don't match, in their degrees. But here, the easier way to go would be the elimination. Now in the test, they're going to be mixed up and you have to make the decision. You're not going to have directions that specifically direct you into the category of substitution or elimination. The directions will just say solve by either elimination or substitution. And you will have to show all steps. It will not be acceptable for you to give a graph as your solution. So please don't try that. The directions will say that. Okay, so what I'm going to do is try to either get rid of my x squareds or get rid of my y squareds. It does not matter which one you go after. Both of these are just as much work as I consider these coefficients. Here I'd have to turn them into tens. You turn them into the numbers that you want them to be by way of multiplication. When you're doing the elimination method, you're going after, you're trying to create opposite signed coefficients in your either your x's or your y's to begin with. That's how the whole technique starts, with you trying to create opposite signed coefficients. And you create those opposite signed coefficients, as I said, by way of multiplication. Okay, so think of the the smallest number that both 2 and 5 go into, and that would be 10. So you'd be trying to create tens right here. And you can do it for either the x's or the y's, whatever you're into. If if for some reason you want to say, oh, this already has the negative and this one already has the positive, so I'm all set with that, fine. You could turn these into 15s. But it's really easy to introduce the negative, so that doesn't really make it any easier. So I'm going to go after tens. That means I want one of them to be a -10, thus the information that I've given you here. Opposite signed coefficients is what's going to get them to eliminate when you add the two equations together. So let's see, if I want this to be let's make this one a -10, then I would multiply this by -5. And if I want this one to be the +10, then I just multiply by 2. I'm going to put here what each thing turns into as I multiply each thing by -5 in the top equation. It's -10 x squared. Then it's -5 times -5, 25 on your y squared term. Then it's -5 times 12, -60. On the bottom equation, multiplying everything by 2 gives you a +10 x squared. Then 2 times 3 is 6 y squared. And then 2 times 92 is 184. And then you add the equations together once you get those opposite signed coefficients. So it's this combined with this, gone. This combined with this, 31y squared. And then this combined with this, 184 take away 60 is 124. Okay, then you're going to go divide off that 31, and you get y squared is equal to 124 divided by 31 is 4. Okay, then you're going to get rid of the square by taking the square root. Same thing here. Report both the positive and negative root. So that's plus or minus 2. So you have two different y values. You have a +2, you have a -2. And once again, you want to find out what is the partner that goes with this. What's the partner that goes with this one? What's the partner that goes with that one? Okay, so now pick an equation to use. Both of the one's just as difficult as the other. You don't have an easier equation here because there's no linear equation, and begin looking for these partners. I'm going to use the top equations. The numbers are a little smaller, but it's your choice. Okay, so it's 2x squared minus 5y squared is equal to 12. And let's see, my y value was 2, so I left a blank spot for y. And then I'm going 2x squared minus 4 times 5. 20 is equal to 12. I'm going to move this -20 over here, at which point it becomes +20. So it's 2x squared is equal to 32. I'm going to divide by 2 on both sides, giving me x squared equal to 16. Taking square root of both sides would give me plus or minus 4. So x is equal to plus or minus 4. All right, so what does that mean? I'm getting two different answers for x, and both of them belong to y equal to 2. I mean, I got these answers because I plugged in this value for y. So what does that mean? It means you got two ordered pairs just off of this y value. When y is 2, you get 4 as well as -4. So there's 4 answers. There's going to be 4 answers here, which means that if you were to graph these two graphs, they would hit in 4 different places. So now continuing with this and doing our work for y equal to -2. Okay, so 2 times x squared, and maybe you can see that some of this work can be cut out at this point. I'm putting in a -2 this time for my y. Because remember, y turned out to be 2. It also turned out to be -2. Still plugging it into this equation right here, but what I've done is instead of putting a 2, I put a -2. Okay, well, how does that change things? I don't think it changes anything, because when you square 2, you get 4. 4 times negative 5 is negative 20. So you literally end up with the same thing at this point that you had in this other equation. I mean, check it out. You had 2x squared minus 20 is equal to 12. You have the same thing here. So how can anything go any differently from there? It's not going to. You're going to get the same values for x. If you keep solving for x, you're going to get just what you got right here. X is equal to plus or minus 4. But that still gives you 2 brand new solutions, because both of these answers belong to y equal to negative 2. So you really do get 2 more answers. When y is equal to negative 2, you get the same x values, 4 and negative 4. So altogether, there are 4 answers. There's positive 4, 2. There's negative 4, 2. There's positive 4, negative 2. And negative 4, negative 2. 4 completely different answers. Okay, so that is 58, which is choice B. 4, 2, negative 4, 2. 4, negative 2, and negative 4, 2. Those are the 4 answers that we got. Okay, moving on to the last 2 problems, which are 59 and 60. So 59, oops, I think I copied it already for us. Okay, again, this is an elimination problem. It is fit for elimination because in your x term, both of them are second degree. In your y term, both of them are second degree. So you can either try to get the x's to go away or the y's to go away. Now, when you look at this, just trying to conserve on the amount of work that you're going to have to put forth, notice that the y's are already ready to go. You have a positive 2 coefficient and a negative 2 coefficient. So you already have negative opposite signed coefficients. So jump right into the addition of the 2 equations where you're combining the 2 equations, because these are going to cancel, which is the whole point of having opposite signed coefficients. 3 plus 1 is 4 on your x squared term. And when you combine 89 and 21, you end up with 60. 8 minus 2 is 6. 9 minus 1 is 8. Then I'm going to divide by 4 here, divide by 4 here, and I'm going to get x squared is equal to, you can see what this is, 68, 17. Okay, so this time we're not going to get a nice integer, it's just plus or minus square root of 17. So you have one solution for x, which is positive square root of 17, and you need a y partner to go with that, or y partners, whatever happens. And you also have x equal to negative square root of 17, and you need a y partner to go with it. All right, so you can plug into either one of these equations. You can plug into 3x squared plus 2y squared equals 89, or x squared minus 2y squared equal to negative 21. I'm going to plug into, just make a choice, whichever one you want to plug into. I'm going to plug into this one. Okay, I'm putting in this for x squared, so it's going to be, and you know that whether you plug in square root of 17 or negative square root of 17, squaring anything that's positive versus that same number that's negative is going to give you the same value. When you square this, off pops the radical and out comes the 17. Then it's minus 2y squared is equal to negative 21. Okay, moving this 17 to the other side, you'd have negative 17. As this positive 17 jumps to the other side, it becomes negative, so that's gone. Combining these, you would have negative 38. You'd have negative 2y over here, negative 2y squared. You'd be dividing by negative 2, likewise over here. You'd end up with y squared is equal to 19. Okay. And then you would take the square root. Don't forget to report both the positive and the negative root when you're solving for anything squared. So one of your solutions for y is positive 19. The other solution is negative 19. So both of these solutions belong to the x value that produced it. And what we plugged in for the x value was square root of 17. Okay, so we have two solutions off this. We have x is equal to square root of 17, producing positive square root of 19 as a y partner. And when x is positive square root of 17, we also got negative square root of 19 as its y partner. However, when you go to do this same thing over here, and instead of plugging in, we had that x could be, let me move this down, that we could plug in either this for x, but also this for x. So this is when we plugged in, and let me, oops, I have an eraser there. This right here is when we plugged in x equal to square root of 17. We plugged in the positive square root. But what difference is it going to make when you plug in negative square root of 17? Because you'd still be plugging it in right here. You would be opening up this x squared. And whether you dump in positive square root of 17 or negative square root of 17, you still get a 17, just like we got right there. You would still get 17 minus 2y squared is equal to negative 21. And if you're going to get that same equation, then ultimately you're going to get the same answers that you had right here. Okay, so y would still be plus or minus square root of 19. But these answers belong to x equal to negative square root of 17. They are paired because that's what we plugged in for x squared right here. We went x squared minus 2y squared equal to negative 21. So here we're plugging in x equal to negative square root of 17. And still getting the same answers because we're plugging in that value for x squared. And whether you square a negative or you square a positive, you get the same thing, which we did. That's 17 here, 17 there. Okay, so this gives you two more answers. When x is negative square root of 17, you get either positive square root of 19, or when x is negative square root of 17, you could also get negative square root of 19. And that is your third and your fourth answer. And so here you have square root of 17 with positive square root of 19 and negative square root of 19, and negative square root of 17 with the same two y coordinates. So for 59, that choice of answer would be choice A. These are all the ordered pairs that we got. Square root of positive square root of 17 with square root of 19, and also negative square root of 19, and negative square root of 17 with square root of 19 and negative square root of 19. Okay, last problem. Thank goodness. Whew. I think this one, I wrote it down already also. copy these twice. I lost my mind at this point. That might have happened sooner than not. Okay, here we go. I put right here that if you want to check out the graph that I created, all I did was go to desmos.com, and I just went to desmos.com, check, and without all this. This is just what you can type in if you want to see my completed graph for this particular problem, which when you click on the points where this graph intersects this one, you get this, which is really square root of 19, and you negative square root of 19, and then that same decimal, positive square root of 19, both paired with 9. And then you get negative. No, I just wrote it for you here in radical form, so those are actually the only two answers. This is equivalent to this. And you can put it in your calculator to check that out. When you put in square root of 19, you get 4.359 approximately. So that's what the calculator gave. It gave you these 2 points at the top of the graph and then down towards the bottom of the graph. The two graphs, this happens to be a circle, and this happens to be a parabola. And down towards the bottom of the graph, the parabola hits at 0, 10. So this was another point of intersection. So there was this one, and this one. There was actually 3 points where it hit. And you can go to that website, but I'll also show you a picture of it. I went to the Desmos site and then I printed it out so that you could see what it looks like. But you still need to be able to show all the algebraic steps for these problems. Don't just say I did it in the graphing calculator, because you will not get any points. Okay, so here we go. We're going to do, I think this one is suited for substitution. And that's because one of your variables has a coefficient of 1 and you could just plug it right in there. Okay, let's see. Now let me check this out and see if there's an easier way to go here, because I want to try and do the least amount of work possible. In place of, let's see, if I wanted to do an equation that had nothing but y's in it, like a y to the first degree and then maybe another y but to the second degree, I could solve for x squared here and bring this to the other side. And that would give me, if I bring this to the other side, give me 100 minus y squared if I pull this to the other side. And I could then take all of that and dump it in for x squared. I think that's what I'm going to do. I'm going to say x squared is equal to, I'm going to pull this to the other side, which would make it negative y squared. So I have 100 minus y squared for this first equation. All I did was move this over here, get 100 minus y squared. I am now going to take this and substitute this for x squared in this bottom equation. So I'm going to go y is equal to, and right in there for x squared, I'm going to use what I got for x squared, 100 minus y squared. 100 minus y squared. And then there was also a negative 10. I just substituted in there for x squared. X squared is equal to this expression. I dumped this in for x squared, and then I carried down the negative 10. But what I have now is an equation that has nothing but y's in it. So if I wanted to factor this, I would just need to bring everything to one side. So everything's pretty much over here. I'll just bring the y over here. And it'll be negative y. So it'll be 0 is equal to negative y squared minus y. I'm going to combine this 100 with the negative 10 to give me 90. I'm going to get rid of this negative leading coefficient, but by dividing this entire expression by negative 1, just to make the factoring procedure easier, just in case we can factor it. Okay, so everything divided by -1 is just going to switch each of these signs. So this will become positive y squared. Negative y divided by -1 is positive y. It just switches the signs of everything in the numerator. And this will be -90. 0 divided by any number is 0. When you try to factor this, you can use guess and check because the coefficient is 1 here. So you're taking the square root of the y squared, asking yourself what two numbers multiply to give you 90, but add up to give you 1. And that would be positive 10 and -9. That times that is -90. This plus this is 1. What zeroes out, the zeros, or in other words, the solutions, would be what zeroes out each of the factors. So that would be y is equal to -10. And also what zeroes this out is y is equal to 9. Okay, now we need the x partners that go with this. What goes with this? What goes with this? All right, so let's see. And there may be more than one x partner, so let's check it out. We can plug into either one of these equations. It doesn't matter which one. I'm going to plug into the bottom equation. That's what I choose. Y is equal to, okay, we're looking for what goes with the -10, what goes with the y value of 9. We're going to be putting these values in for y. So let me just copy the equation that I've chosen to work with first. I have chosen to use the bottom equation. There was two equations, this one and this one. So I've chosen equation 2. I have a y value to plug in, so I'd be putting in a -10 there and then solving for x. Okay, so let's see. If I was going to solve this, I'd have to bring this -10 over there, thereby causing it to become positive 10, and then it would not be on this side anymore. I would just have x squared equal to 0. By the time I take the square root here, I'd have to take the square root here. And I would say plus or minus, but 0 is the only number that is signless. It doesn't come in a positive and negative form. It is just 0. So what was the y value that I just plugged in? -10 was plugged in for y. So x turns out to be 0 because I plugged in -10 for y. That is one of the answers, and it will show on the graph that I've created on the Desmos site. Okay, now let's try 9. Using this same equation again, y is equal to, I like to write the equation first just so you can completely follow me, and you should do the same thing. Organize your work so that it's legible, so that I can follow your train of thought. This time I'm plugging in a y value of 9 as opposed to a y value of -10, which I already finished. So I'm going to put a 9 here. I'm going to put an x squared here and a -10 here, just bringing down these two terms. I'm going to move the -10 to the other side, just like I did when I solved this. Only this time you don't get a 0. You get x squared is equal to 19, so that when you do take the square root, yes, you must report the positive and the negative root. So this will be x is equal to plus or minus 19 when using a y value of 9. So that suggests 2 more solutions. When using a y value of 9, that produces a x partner of positive square root of 19. And it also produces, when using 9, a negative square root of 19 x partner. And so you have the 3 answers. And those are the answers that I stated right up here. This shows on the graph, this shows on the graph, and this shows on the graph. Let me show you a picture of what that graph looks like. Okay, all you'll do is go to desmos.com, stick in those two equations as is. That's part of the beauty of using that site. And then you'll push graph. And when you push graph, this is the picture. This point right here is the 0, -10. That is one place that this parabola hits the circle. And then this point that you're seeing right here, that was the negative square root of 19, which is about it's about negative 4.35, about negative 4.4, and it's 9 units up in the air. So that's this point right here. Negative square root of 19, which is really about negative 4.3. And you can see that this is not even at negative 5. This is about negative 4, over negative 4.3-ish. And then it's 9 units up in the air, just like you see right there. And you can see that's at 9. Likewise, this point of intersection is at positive 4.3. It's a little bit past 4. About 4.3 is what square root of 19 is. And it's 9 units up in the air. So just a way to verify the answer, but it does not serve as your work. We're trying to see whether you know the algebra that goes with finding the solution. Okay, that concludes the last batch of problems on the practice test, all the way up through 60.